Okay, welcome to class 11, and today in concurrency we're going to talk a little bit about multiprocessing as opposed to multi-threading. So far in this class what we've been doing is lots with multi-threading. Multiprocessing, while related and very similar, it's another way to have concurrency, is a little bit different, and we're going to talk about why. Alright, so first off, let's look at, and this is a very dense slide, which I apologize for, but I wanted to have it all visible on one page here. But what's the difference between threads and processes? So with multi-threading, each processor, or one processor is handling multiple tasks. In other words, we have one processor that's kind of switching between things. And this isn't true for all programming languages or environments. It is specifically true, or especially true, with threads in Python. And the reason for that is in Python, you have a single Python interpreter that's responsible for managing all those threads. And that single Python interpreter has to run in one process on one processor. And it actually has this, so it's one Python interpreter that's switching between those threads and running them all. And that Python interpreter, the way the Python is implemented, it has what's called the GIL, or Global Interpreter Lock. And that makes it really difficult to make use of multiple cores and multiple CPUs because you have one interpreter that's saying, it's your turn. Sorry, the dog is trying to pull my laptop off the table because he's fighting with a cat. But anyway, the global interpreter lock basically says it's your turn. It locks out everybody else, and then that one interpreter is doing the switching. And so it's difficult with Python using threading to have a lot of overlapped processes with multiple cores doing multiple things at one time. So it's kind of like a single cook, meaning the single Python interpreter in the kitchen switching between tasks, getting things done. Multiprocessing, on the other hand, makes use of multiple processors or multiple cores within one processor, and it essentially has, rather than one Python interpreter running in one process, it has a duplicate of that. So you can have separate processes, each with their own Python interpreter running in it. So that's kind of like multiple cooks in the kitchen, or a better way to think about it is multiple cooks, each in their own multiple kitchens. So notice how much more efficient that could be. But it's a little more complicated because of that. Let's take a quick look at the overview of the differences. So here's a graphic that kind of shows you what multi-threading is. We have one process, meaning one Python interpreter that has the code. It's got any files that are opened or for reading or writing can be shared amongst the threads. The data, in this case global variables, can be shared amongst the threads. They all are just running in one process together. And it's up to the Python interpreter code that's running to switch between the threads and keep track of who's doing what. And in the case of all of them accessing global variables, if you have something like a lock, that becomes a global as well that's shared between the threads, or you have a condition variable that's up here. They can all access it and use it. And so you get synchronization mechanisms, communication mechanisms, global variables with shared data. All of them are really just running in one processor, or one process on one processor, and it's being switched between them. Doesn't mean that it's not a good thing to do. It can be very natural to do that. But with threads, they're all in one process with one Python interpreter running it. Now, in the case of multiprocessing, the global variables, you basically have duplicates of that. Some processes might have more than one thread, but the processes themselves are guaranteed to have one thread. But notice there's nothing that's shared between them. The code is separate. Any files they open for reading or writing are separate. Any data they have, like global variables, are by the nature of processes separate and can't be shared. There's no way for them to share it, at least built in the way there is with threading. So that means how we get these things to cooperate or communicate or synchronize, that has to be done differently as well. So the end idea here, processes are entirely separate from one another. That means they can't have global variables that they share, like with the ornamental garden problem, count plus equal 1 on entry, count minus equal 1 on exit. We also can't have shared object references that are easily accessible between them. And when a process is created, it kind of clones the parent's process, both the code and the data. So when we spawn a process, it makes an entire copy of the original program. And that fact that it's kind of a clone of the original means that if there are global variables, there's now a copy of those global variables or those shared object references, but it's completely separate. They're isolated. So a change to this one is not going to also make a change to the other one. So that separation is going to create some problems that we need to address. The first of them is if you're using idle to do your development, calls to the print function aren't going to show up in the console if things are printed from the sub processes. And that just has to do with how idle works and how it gets that data. We'll talk about how to address these problems in a second. Another problem that will need to be addressed is we'll need to protect that main process code so it doesn't run when those clone and make copies. Python has this feature that when a code module is loaded into memory by the Python interpreter, it will run any code that's in the main section of the program. And in other words, as it loads that program, it runs the things that aren't indented underneath a function or aren't protected in some way. We're going to need to protect that because we don't want it to load a copy and then run the code, and then that code then loads a copy which runs the code. We'll look at why that's a problem here in a second. Also, we need to figure out how to make those things cooperate or communicate or synchronize without using shared variables and or shared object references. And that means we have to work a little bit differently than we do with threads to truly take advantage of multiple cores in the CPU. All right, first off, let's fix these one at a time. The print statement and idle not working correctly. And the problem there is that print calls won't show up on the console in idle except for in the main thread. So if your process needs to print then from the sub-processes, then you can run the program directly in a console window. And how would you do that? Well, in other words, you do the following. You can either double-click the .py program to execute it, and that'll run it in a console rather than in idle. Or I don't think this is a problem if you're using something like another IDE other than idle. So if you're using PyCharm, I think it'll work fine without having to do this. But you can still double-click the .py program to execute it, or you can run a command shell by going to run command, make sure you're in the directory where your py file is, and then you can just type Python, whatever the name of the file is, .py, and run it. It'll execute it right there. When I test mine, I usually do it this way. The reason being I have more than one Python version on here, and I want to make sure I have the right version associated with Python. But you can do it either way, or you could just use something like PyCharm. But I haven't tested PyCharm. I think it works though. Now, the second one, how do you protect the main process? The way that you do that is you don't want the main code to run in the copy threads, because then you could have, it's kind of like I don't know if you've ever seen that Disney movie Fantasia with the Sorcerer's Apprentice, where Mickey Mouse tries to destroy the broom and it breaks in half and makes 2, and then he breaks those in half and it makes 4, and it just gets out of control. But that's the kind of thing that can happen if you don't protect that code there, because when Python makes a clone, if it runs the code that made the clone, it can make another clone. And to prevent what's called a process bomb or fork bomb from happening, when they made Python and they made the multiprocessing module, they made it so you have to protect that main thread code, or it won't spawn the thread. So in other words, rather than having things get out of control with processes, making processes, they've actually prevented that. So you have to protect your code. If you get a weird error that says something about code must be inside of main protection or something like that, that's the reason. So the way you'd set that up is you have your imports at the top, any definitions you have here, including variables and other things that you have, functions, classes, whatever. And then you have the main thread code protected inside this if statement. So you'd say if underscore name underscore equal underscore main underscore. So in other words, if this is the main thread, it'll have that name. And if that's the case, then it'll run this code. If it's not the main thread, it'll just not do any of that. It might import this stuff and do that, it'll skip over that stuff there. So why do that? Again, for every process that is spawned, it has to make a clone of the original. And the way Python works is when it loads that program, the same program into memory, as in a clone, we do not want it to run the main code as it loads it in. So you have to have this protection. We'll look at an example here in a second. All right, the third problem is global variables and object references that are shared. We can't have. There are no shared variables or object references in processes because every process is a copy or a clone of the original, but with the target function being executed. We'll look at that in a second. And so the fix here is to use some sort of synchronization or communication mechanism that works with multiprocessing. And a lot of those, when we dig into those, look, they're going to be familiar. They're the same things we saw with threading, but we have to, but they work differently behind the curtain, meaning under the hood, they work a little bit differently because they have to talk between processes rather than sharing an object. And there's another thing we have to use them a little bit differently as well, which we'll see. And some of that is going to be new and unfamiliar to us. It's going to look a little different than how we dealt with those things in or using threads. All right, so before we look at that, let's look at that process separation in action. So here's some code, and let me see if I have this code handy where we can actually run it live and see it actually do something. Yeah, I do. So I'll switch over to that here in just a second, but let me first show you what this code does. So this code imports multiprocessing instead of threading. There's a global variable that we created called SumGlobal. Starts out at 0. Then here's the function I'm going to use for a process. It just says, hey, there's a global variable SumGlobal. SumGlobal plus equal 1. Add 1 to it. I'm a child process. And then down here, we make a list of 10 of these processes. The target is my process. Notice how similar this looks to threading. But instead of saying threading.thread, we say multiprocessing.process. That creates a process, and then I'm adding it to this list. We could have done that all in one line, but to make it more clear, I did it 2 separate lines. And then I start all the processes. I wait for them all to complete, and then I print out the result of the global. Now, if this was a thread-based program, we're starting 10 threads. They're each adding 1 to the global. There's no protection around this, so we expect it to be 10 or maybe something less if they stepped on each other's toes as they were doing that. But when we actually run this, let me switch over to that so you can actually see this thing run. So give me just a second here to switch over to that. So there it is. I run that program. Notice I get a result of 0. And the reason I'm getting that result of 0, you might think, well, they're not running. They're supposed to print I'm the child process. Let's actually run that the other way, which I already did right here. Double-clicked it. We get this. Or actually, I ran this one from the command line. All of them are running. They're all 10 running. They all have to be adding to that global, but somehow it still comes out as 0. And the reason for that is because, let's go back and look at that code. So give me just a second here. So there's the code. Looking at that code, it might become clear that it's when each of them gets spawned, they make a complete copy of everything, including that global variable. So every process has its own global variable called SumGlobal, and since they get cloned here, their copy all comes out as 0 because each clone is the same as the original, so the memory is 0 for all of them, including the main. And even though these changed their global variable and added 1 to it, it doesn't change the other ones because they're all completely separate. Remember that diagram where the memory is completely separate for processes. It's all isolated in a different place. So there's what the output in idle came out as. There's what it came out in the console. We get to see they all ran, but we still get 0 no matter what because it's a copy of a global that was started out at 0. So if we copy 0, we get 0. The main thread still has its original copy that was 0, and the main thread never changed SumGlobal anywhere in it. So it's still 0, so we just get 0 printed out at the end, just like we see. So we cannot use shared variables like this. Now, that means we have to use some kind of synchronization or communication mechanism to get those processes to share things or communicate with each other. All right, so to get them to do that, we need to use some sort of mechanism to share data or return a value. If we want to synchronize between them, we need to use a synchronization mechanism. So we're going to look at a few of those today. And one thing to note is there are other ways to make processes besides this multiprocessing.process, but they're OS specific or operating system specific, meaning it would work differently on Linux and Mac than it would on Windows or something else. But this threading is now part of the Python's standard modules, so that will, or not threading, but multiprocessing is as well. So that will work on any system that has Python installed that's a recent enough version to support multiprocessing. So it's in OS independent. So that's what we're going to focus on today. All right, now the mechanisms for multiprocessing are going to look really familiar. Lock, rlock, semaphore, bounded semaphore condition, barrier, event queue. Those all exist. One difference, though, is that these are not in threading. So we don't use threading.lock. We would use multiprocessing.lock. So that's the first thing. We would use multiprocessing.lock or multiprocessing.queue, multiprocessing.barrier, whatever, for each one when we're working with multiple processes. Now, there's also another thing that should be mentioned here, and that is because there are no shared object references, we have to use those objects a little bit differently than we did with threads. So we'll look at that a little more in the next slides here. Now, before we do that, though, there are a couple other things, like, for example, multiprocessing.cpu_count. That will return the number of cores or CPUs that your system has. And just as a quick side, let me switch back over to this Python shell for a second and let you look at that, how that works. So here we are. Let me go into that shell. Let me do import multiprocessing. So my laptop has 8 cores in it. Your laptop might have a different number. It might have 12, might have 16, might have 6, might have 3, might have 2. If it's a really old laptop, it might even just have 1. But this multiprocessing.cpu count is telling me I have the CPU inside of this Asus laptop has 8 cores inside of it. And this is a Core i7 or something, I believe, in this an Intel processor. But it might have even more. It could have 24 cores in your machine, or more. Depends on the processor you have. But that's telling me how many things I can really truly overlap. Now, one cool thing about the multiprocessing module is even if you don't have enough processes or processors for the number of processes, it doesn't matter. You can still make 100 processes if you want. One thing to note about processes versus threads, though, is there's more overhead with creating another process. In other words, spawning a process has overhead because it has to make an entire clone of the main process, which takes time, and it takes a bunch of operating system overhead to do that. And it has to fire up another Python interpreter to run that code. So there's more overhead with making a process than there is with making a thread. But the advantage is after you've made that process, it can truly overlap and take advantage of those multiple processors that we have. So for CPU-bound operations, multiprocessing is good. Now, one thing to remember, though, that we should keep in mind is that because there are no shared object references, we have to use those synchronization and communication objects in multiprocessing differently than we did with threads. And we said more on that in a bit. Well, before we get into the more on that in a bit and how we're going to use those, let's talk about why. So why do we have to use those differently than we did with threading? And the answer is because separate processes have completely separate and isolated memory. We can't just share those object references. And I have a little sad face there because that makes some things a little more difficult. We can't just, but it also makes things a little safer, and that's why it's completely separate like that. It makes it so the shared memory problems go away, and we have to communicate or synchronize using those mechanisms. But we have to do so a little bit differently. Let's look at how. Okay, so here's a program where we try to use multiprocessing.q. And this process, which we spawn right here with P1, we start it, we join it. Let's say we want to return value from that. So we do some stuff, and then we do q1.put1. So we're putting the number 1 into that queue. And then in our main thread, after process 1 has completed, we do value 1 q1.get. So we try to get the value 1 that this process put into the queue. We try to get that out of the queue. And then we just print whatever. So this is whatever came back. So in this case, it should say value equal 1. But when we run this program, the main thread, the main process, locks up. It never gets anything back from Q1. And you might think, well, why not? It's clearly putting it in there. We clearly started it. We could even print stuff out and see it running. Why am I never getting anything back? And again, the reason for that, just like the reason for that sum global we had in the other program always giving 0, is because when this makes a clone of this process, we have a clone of that Q1. It has this completely separate queue. Each process has its own queue. So that doesn't work. So when I do a q1.get, nothing is ever put into it in the main. So we're kind of stuck. We never get anything into Q1, so we'll sit here waiting forever to get something that will never get put in there. And this is putting something into Q1, but then nothing ever happens with it. So the question is, well, this is a little more complicated. How do we actually give this process the ability to put things into the queue that can be taken out or gotten from another process? And the answer to that is we just have to change our way of using that. Rather than trying to use a global, since globals don't work, it would work with threads, but it won't work with processes. It locks up. Why? We already talked about why. We've made a copy of the queue. The stuff gets put in by the sub-process, the child process, the parent process, the main tries to take something out, but since it's a copy, nothing ever gets put into the original, only into the copy. So we need to change how we do that. And so the answer is all global variables are copies, including that Q1. So that Q1 variable is a separate copy. It's a completely separate queue object. So the main process has a Q1, a queue Q1. Process P1 has a separate copy of a queue called Q1. So the question is, how do we fix that? So here's a fixed example of that. And to fix that, essentially what we're going to do is we need to pass the reference to that queue to the process when we create it. So in other words, when we create the process, we're going to say, here's the reference to this queue object that you're going to access. And then that means we need to make that process accept that kind of accessor reference in order to access it. So now here, rather than a copy of a global, notice we have no more globals. So the first thing we did is we moved Q1 down to be only defined in the main, right here. So if we're in the main, define Q1. But now to give those sub-processes access to that, we're going to pass that Q1 that we made in the main. There's only one of them now. There's not a global. That one that we made in the main, we're passing the reference to it, or to this function as an argument. And we do that with args equal. There it is there. And now we do p1.start, p1.join. Now when this puts it in, it's putting into the queue that was created in the main, because we passed the reference to it. And now we can get the value. So this one will actually complete and get the value 1. And the idea here is that those changes we made, which I highlighted there so you can see them more easily, allows the sub-process to stick things into the queue that was defined in the main, and the main one can now pull things out of that queue. So a little bit different way than we did things with threading. Now this technique would also work in threading, so if you want something that worked with both threading and multiprocessing, you could do that the same way, but you have to do it this way for multiprocessing. All right. So that's how you would allow multiple processes to access other mechanisms as well. So all of those mechanisms we looked at, lock, rlock, semaphore, bounded semaphore, condition objects, barriers, queues, events, all of those have an analog in multiprocessing, but you would have to do it this kind of a similar way to what we did here. And the way that would be is you create the mechanisms in the main process only. In other words, it has to be inside of this if part right here. And then you pass the reference to the mechanism to the spawn process as an argument, just like we did here. And then you would access those mechanisms within the sub-processes or the main process, and now you're accessing the same thing that you're referencing. And the one thing to keep in mind, don't accidentally try to use shared variables or shared object references like you did with threading, because it'll kind of fail silently. It just won't work. Because it'll make a copy, the code will still run, it won't throw exceptions, but it's not going to communicate or synchronize because they're completely independent at that point. The only way to do it is like we did here. Sort of the only way to do it. There's some other options, but we're not going to concern ourselves with those right now. All right, so that's it for today. Relatively short lecture. One thing I do want to announce is we have the midterm exam that we need to consider coming up. I'll probably mention that a little more on Thursday, but I think we're going to have that when we get back from spring break. So next week is spring break. The week after that, I believe we're going to have the thing. So watch for the announcement about that. I will post a study guide that has an outline of all the stuff we've covered so far for you to look at. But look for that announcement. I'll probably post that, the study guide and the announcement of when the midterm will be. I'll probably post that on Thursday. It'll either be the Tuesday when we get back, or it'll be the Thursday after we get back. It'll be one of those two options for when the midterm will be. So anyway, stay safe, wear a mask, social distance, whatever, stay out of trouble. Finish the labs I gave you. I'm not going to give you a new lab tonight. We're going to have a lab doing some multiprocessing stuff coming up. But go ahead and finish what you're working on. See if you can get all that stuff tied up, because I want to kind of have the slate cleared by the time we move into the midterm, so I'm not going to overload you with more stuff right now. All right, that's it. Everybody have a good night. Or afternoon, depending on which section you're in. Stay safe. And if you're interested in the dog that was attacking the cat, he's down here sleeping in front of the fire now, celebrating a job well done for chasing the cat out of the room. All right, bye.